Hello, I'm Brian Young, and today we're doing Module 26210, Circuit Breakers and Fuses. Let's get started. Module 26210, Circuit Breakers and Fuses. Successful completion of this module prepares you to do the following: describe the function of overcurrent protective devices, identify and describe circuit breakers and their characteristics, explain how to size and select fuses. And then there are performance tasks that your instructor will want you to do. So all electrical circuits and their components are subject to destructive overcurrent conditions resulting from a wide variety of causes. Reliable protective devices prevent or minimize costly damage to conductors, transformers, motors, and the many other components that comprise the complete electrical system. Circuit breakers and fuses are two common protective devices used in electrical circuits. This module describes the operating principles of circuit breakers and fuses and explains how they are applied in today's electrical systems. So, and here it says, describe the function of overcurrent protective devices, describe various overcurrent conditions, state the NEC requirements for overcurrent protective devices. You got a string of lights. Each bulb is a 100-watt bulb, and your foreman tells you that the far corner of the room is a little too dark. You need to add some lighting. So you take some screw shells, some temporary lighting, and you attach them to the stringer. And you screw in one 100-watt light bulb. You screw in another 100-watt light bulb. And you screw in a 1200-watt light bulb. And you get to the point where you screw one lamp in and you trip the circuit breaker. So you take that last bulb out and you go reset the circuit breaker. That's an overcurrent. Nothing happened, nothing blew up, nobody died, nobody got hurt, but that was an overcurrent. It was a current greater than the rating of the circuit. So the overcurrent protective device did its job and disconnected the power from that circuit. Because whatever it was set at, if it was set at 15 amps and you got to 16 amps, the circuit breaker decided that's too much current for this circuit, and it shut off the circuit. It tripped. Did exactly what it was supposed to do. Now, later on, you'll learn that lighting is considered a continuous load, and we shouldn't put more than 80% on that circuit. So if it's a 15 amp circuit breaker, we shouldn't put more than 12 amps on it. So you can't just start adding screw shells and screwing in temporary lighting 100 watts at a time and then see when it trips and then just back off by one. It needs to be figured out mathematically. You decide what the load should be, and then you go below that. And if you need another circuit, you put another circuit breaker in the temporary panel, and you put another stringer of lights up. Okay. That's an overcurrent. There are all different sorts of overcurrents. Some are not destructive, some are. Someone's working in a box and they accidentally slip and their screwdriver goes in and hits between two buses. That's also an overcurrent, but that's a short circuit. It's a different type of overcurrent. That short circuit will allow a lot of current to flow in the circuit, and it'll trip the circuit breaker almost instantaneously. Some circuit breakers are current limiting, and they will act within 1/2 cycle. So one amplitude of the sine wave, they'll turn off. Others might take 3 or 4 complete cycles before they will trip. But let's see what the book says. Let's go into the book. It says all electrical circuits are and their related components are subject to destructive overcurrent conditions, harsh environments, general deterioration, accidents, damage from natural causes, and overloading of an electrical circuit can all be possible causes. To protect electrical systems from abnormal operating conditions and their consequences, reliable overcurrent protection is needed to avoid costly losses. So we limit the amount of current on a conductor because an overcurrent will cause heating and it will deteriorate the insulation of that wire. So if you have a wire and that wire is good for 20 amps and we put 40 amps on it and we use it for a couple of years, the insulation is going to become brittle it will eventually, if it's moved, crack and split. Pieces of it will fall off, leaving bare conductor, which is dangerous to personnel and dangerous to equipment because it could touch a metal box or pipe. So what we're trying to do is prolong the life of the wire by limiting the amount of current, thus the amount of heat on that insulation. Overcurrent conditions. An overcurrent condition can be an overload current, a short circuit current, or a ground fault. Overload, often referred to simply as an overload, is an extensive current relative to a normal operating current but is confined by the normal conductive path. A short circuit is where the current has taken a shortcut. It's a very common cause of electrical problems. A short circuit is an undesired current path that allows electrical current to bypass the load on a circuit. It's typically an unintended connection between two conductors. If an unintended connection occurs between a wire and a grounded object, such as a metal frame or motor, it's considered a ground fault. So anytime you go to ground, it's a ground fault. If an ungrounded conductor goes to ground, it's a ground fault. If a neutral conductor goes to ground, it's a ground fault. If an ungrounded conductor and the grounded conductor, usually the neutral, if they touch, if they come into contact, that's a short circuit. Or if two ungrounded conductors of different potential touch, that's a short circuit. So we have short circuits, we have ground faults, anything dealing with ground or metal or pipe, it's ground fault, or overcurrent. That's the least destructive of the three. It just means that we put too much current on that circuit and the circuit breaker tripped. All right. So here are the wires, and as we stated earlier, that insulation became brittle and cracked off, and now you've got two ungrounded conductors touching each other. That's a short circuit. Overloads most often reach between 1 and 6 times the normal current level. Usually they're caused by harmless temporary surge currents that occur when motors are started up or transformers are energized. Because some are expected and very short-lived, any temperature rise is trivial and has no harmful effect on circuit components. So anytime we start a motor, there's an inrush current, sometimes as much as 7 times the running current of that motor. Anytime we turn on a transformer, even a lighting panel, if it's incandescent lights, there's going to be an inrush current until the filament heats up and raises the resistance of that lamp to a point where the operating current comes down to normal. It's very short-lived. We're talking about milliseconds. I'm not even going to say half a second. I mean, this happens very quickly. With the motor, if it took 3 seconds for that motor to come up to speed, I'd say there was something holding back on it. Maybe it is trying to move water. Maybe it's moving a pump and that pump is moving water, so it takes a couple of seconds. But it doesn't take a motor 30 seconds to get up to speed. All right. So in that time, there is an overcurrent, but it's okay. We accept that and we plan for it. We're going to use circuit breakers that are inverse time, meaning that the amount of short circuit current, or I shouldn't say short circuit, the amount of overload current, overcurrent, is 5 to 6 times the expected current, and it only occurs for less than a half a second. That inverse time circuit breaker will allow, I want to say it'll allow twice its rated current for 30 seconds. So if it's a 20 amp circuit breaker, it'll allow 40 amps to flow for 30 seconds, I think is what they said. We'll find out. But if there's 1,000 amps flowing on it, it'll trip almost instantaneously. The higher the fault current, the shorter the time duration that it takes that circuit breaker to trip. That's what they mean by inverse time. The higher the fault current, the shorter the amount of time that it takes to trip. So it's inverse time relationship to the amount of fault current. And that way the motor can come up to speed. That way the lights can get to full brightness. That way the transformer can start up and start feeding loads. And the secondary counter electromotive force is going to keep the primary current low in that transformer. Therefore, it's important for protective devices do not react to those expected momentary conditions. Continuous overloads can result from motor defects such as worn bearings. Right, that's a highlight. Overloaded equipment, too many loads on a single circuit. Sustained overloads are destructive and must be stopped by protective devices before the damage to the electrical distribution system or affect the system loads. However, since they're of relatively low magnitude compared to short circuit events, interruption of the overload current within a few seconds will generally prevent significant damage. A sustained overload current results in overheated conductors, which can damage the insulation. Insulation damage can eventually result in more short circuit events if not prevented. So we have fuses and circuit breakers. You probably already know that fuses are not renewable. Overcurrent protective devices with fusible components that melt are thereby severed by the passage of current beyond their rating. And circuit breakers, devices designed to open and close a circuit manually or automatically when a predetermined level of current exists without damage to themselves when properly applied. Uh, Fuses and circuit breakers are two overload protective devices that are normally used in electrical circuits to prevent damage from excessive current. Function of circuit breakers and fuses can be compared to that of I don't equate electricity and water. Most all of your textbooks will. I don't like it, so I'm just going to move on. I don't try to talk about a dam in a river and the amount of water flowing is the current and the pressure. Water pressure is the voltage. I don't go there. Anyway, that's just me. NEC regulations are some critical NEC sections you should become familiar with. While some of the content is summarized here, remember that it's important to consult the NEC directly for accurate and complete information. The following are not only important NEC requirements related to overcurrent protection, they're considered by many to be the most important. So, Section 110.3b says installation and use equipment that's listed, labeled, or identified for a particular use must be installed and used in accordance with any related instructions. So we have to follow the manufacturer's instructions when we're installing any equipment that has been labeled or listed. And labeled and listed is a nationally recognized testing laboratory like Underwriters Laboratory. 110.9 interrupting rating. Equipment intended to interrupt overcurrent events must have an interrupting rating that's at least equal to the current available at the equipment line terminals. So your interrupting rating is the maximum amount of current that that circuit breaker or fuse can interrupt without exploding. So if it's a 20 amp circuit breaker, at 21 amps it starts thinking about tripping. At 100 amps, it's going to trip within a couple of seconds. And at 1,000 amps, it's going to trip almost instantaneously. But what if there are 10,000 amps of fault current? Your interrupting rating says, I can interrupt that 10,000 amps of fault current. If I see 10,000 amps of fault current, I will open the circuit and I won't explode in your face. If we subject that 10,000 amp interrupting rating circuit breaker to 50,000 amps of fault current, it'll come apart. It becomes a grenade. There's shrapnel involved. It's a very dangerous situation. So every device intended to interrupt a fault current must have a rating of what it can interrupt safely. And the minimum for a circuit breaker is 5,000 amps. If you don't see a rating on it, like at your house, probably the ones you buy at Home Depot are 5,000 amps of interrupting rating, because the line transformer that feeds your house will not deliver more than 5,000 amps. If you get to where you're trying to use 5,000 amps, the jacks on the transformer out on the pole are going to blow. So they will protect you. If there is fault current available that's higher than that, then the circuit breaker or the fuse has to be labeled with what its interrupting rating is. fuses start at 10,000 amps of interrupting rating. Circuit breakers start at 5,000. Fuses start at 10,000. So for that reason, a lot of the old timers like fuses better than circuit breakers, and they actually want fuses in their house rather than circuit breakers. I'd rather have a circuit breaker because they're resettable. So, but fuses are very safe. If somebody has fuses and a company says to them, "Oh, you've got to change out this panel because you've got fuses," that's not true. You can have fuses. You can continue using fuses. And if you're blowing a fuse, there's a problem. Find out what the problem is and fix it. Don't just keep putting fuses in your fuse panel. Anyway, uh, Section 110.10, circuit impedance, short circuit current rating, and other characteristics. The overcurrent protective device, the total impedance, the component short circuit current ratings, and other characteristics of a circuit requiring protection must be selected and coordinated to prevent the protective devices to function without extensive damage to circuit components. For this purpose, the fault is assumed to be between two or more circuit conductors or between any circuit conductor and the equipment grounding conductor as permitted in NEC section 250.118. Section 240.1 scope informational note says overcurrent protection is provided to open a circuit when the current could cause extensive or dangerous temperature rise in conductors or their insulation. See also section 110.9 and 110.10 for additional requirements related to interrupting ratings and protection against fault current. NEC Article 100 defines overcurrent protective device, current limiting. A current limiting overcurrent protective device is a device that reduces the current in a faulted circuit to a level substantially less than that possible if the device were replaced with a solid conductor or similar impedance. That's a horrible definition. A current limiting overcurrent protective device is one that limits the fault current to 1/2 cycle. So within 1/2 cycle, that overcurrent protection device will activate. It'll either open if it's a circuit breaker or it'll burn if it's a fuse, and it will not allow that fault current to hit 5 or 6 peak voltages when the current is at its highest. NEC section 240.83c, here's a highlight. It says interrupting rating. Every circuit breaker with an interrupting rating other than 5,000 amps must display its interrupting rating. So 5,000 is the least. Anything higher than that, it'll be written on the circuit breaker. All right. NEC section 240.83 voltage marking. The circuit breakers and fuses are to be used in their rated voltage. You can't use them at a higher voltage. You could use them at a lower voltage. But like it was explained to me, a 600 amp fuse is very expensive. You don't want to put a 600 amp fuse in a 240 volt circuit. You want to use a 250 amp volt fuse, excuse me. 240.85 application. A circuit breaker with a specific voltage rating, such as 240 volts, can be applied in any circuit in which the nominal voltage does not exceed the breaker's voltage rating. Further, a two-pole circuit breaker cannot be used to protect a three-phase corner grounded delta unless it's clearly marked as suitable for use in both single-phase and three-phase circuits. All right. And then the last one is 250.4A1, electrical system grounding. I'll let you read that one. Section 1 review. It says worn or damaged motor bearings can cause A. What is it? All right. Where the NEC would you find information on circuit breaker applications? Look in the table of contents. Look for overcurrent protection.